Well, hey there, guys. So today, I want to talk about temperature. And we've talked a little bit about it, but I want to actually go through the theoretical underpinnings of what is temperature. How are we going to define it so that we can talk about it for this course? And the way I want to start is really just picking right up where we left off, which was looking at process diagrams or state diagrams. And to refresh your memory, what that was is a coordinate system with one property here, so let's just call this property A, and another property here, property B. So a property on each axis, and this can be any property of a system that we care to talk about. So when we're going to look at a system, we're going to measure both properties, property A and property B, and we're going to determine where on this grid can we put a point relating to that current state of that system. So how much of property A does it have? Maybe it's got that much. How much property B does it have? Let's say that much. And then we just extrapolate out like this, and that is where we plot our point. And this point represents the current state of our system. So that's kind of where we left off. And like I said, I want to emphasize that we can use any property of a system and plot a chart like this. But for this course, there's going to be three that we're mostly going to focus on. And that is temperature, pressure, and volume. So most of the charts that we make like this are going to involve those variables. So for instance, I'll just list out the options that we may be using. Actually, we will be definitely using these. So first of all, there's pressure versus volume. Okay, we can put pressure on this axis and volume on this axis, volume along the x-axis. We could do, pressure versus temperature. If we wanted to put temperature on this axis, we could do temperature versus volume. Oh, and I said I would use the little hook on the V for my volume for now. And then one other option that we have, these options plot two variables against each other. So we have two axes to our graph. If we wanted to think about a 3D graph with another axis that comes in and out of the board, okay, like this, coming in and out, then we have 3D space and we could plot three variables. So on a 3D graph, we could do all three. Pressure versus temperature versus volume. And that's something that actually turns out to be incredibly useful. But it's harder to visualize because it's 3D. So these are really graphs that we're going to be talking about a lot and utilizing a lot. And so even though we can plot any variable, any property versus any other property, these are the most useful ones. That's why I want to emphasize them. And so you'll notice these all involve three variables: pressure, temperature, and volume. And so I want to spend kind of a little mini lecture talking about pressure and temperature. Volume, I think, is pretty intuitive. I probably belabored the point a lot last time about what volume is, and it's something that we have a very good sense of. And so I'm not going to go into a lot of detail about volume. You guys kind of understand what volume is. The one thing to make sure that you're studying up on is the idea of specific volume. So I'll just write that again. Specific volume is a lowercase letter, and it's the volume divided by the mass. And then there's specific molar volume, which we saw introduced in our meeting. And that is just the same lowercase letter with a bar over it. And that's the total volume divided by the number of moles. Okay? So these are separate. This is one thing, this is another thing. All right? So those are the concepts involved with the volume, but we know kind of what volume is. So that brings us to the question of what temperature is. All right? So let's talk about temperature. Inside any system, if I draw out my system and it's going to contain some volume, so it's going to be my best attempt at a three-dimensional box here, I'm going to zoom right in. Keep zooming in, all right? Zooming into this system until I can see the individual molecules. So maybe it's just monatomic. Maybe there's a single atom, like, free hydrogen or helium or something like that. But maybe there's, let's say, molecular hydrogen, which is two atoms, and in physics, we draw a little spring in between. This is, if you have chemistry background, this is our representation of a covalent bond. And it turns out that the potential for a spring, which you may have learned about last year, spring potential does a pretty good job of replicating the covalent bond. We're not going to get into those details, but needless to say, that's why I'm drawing a spring here. So it can be something simple like this for our molecule, or you guys have seen the crazy diagrams that chemists sometimes have. We can have something just nuts like this, some crazy molecule, okay? I'm just making that shape up. This would all be one molecule. So this is what our particle is, our level of particle. We're not delving inside the atoms to look at subatomic stuff like quarks and gluons. We're just looking at one molecule being one particle, all right? So no matter how crazy these things get, right now, I'm just gonna draw dots. All right? So this box is full of some sort of gas or fluid or any substance. It's made up of particles. Now these things are moving, okay? And as they move, they wiggle a little bit. So if I zoom in to the level of this one particle, it might be doing something like this, okay? And I'll put a big arrowhead because it's moving. So you see it's moving through space and it's wiggling. Now, it's possible that this particle has a general direction in which it's headed. So notice that as I kind of wiggle, I went in and out and back and forth. But this thing was kind of headed from here to here, all right? It kind of was moving in a general direction. If this is the case, that it's moving in a general direction, when we want to talk about temperature, we need to not include that general direction. So here's what I want you to think of. Imagine, and there are actually mathematical ways to formalize what I'm saying. You could actually do a calculation to do what I'm about to say, all right? But just imagine it, that we could take this arrow that's all wiggly and somehow subtract off this arrow. What you might end up with is something that looks like this. Okay, it's just squiggling up all on top of itself. We've taken its wiggly path that's sort of wiggling but tending in one direction, and we've just gotten rid of that overall tendency. So that's the first point, is that if a bunch of molecules are all sort of moving in the same direction over time, there's some sort of flow, then that isn't included in what we're talking about when we talk about temperature being due to movement of molecules. It's really only due to the wiggling of molecules, okay? Now, so that's point number one. Second point with temperature is the fact that it really only has to do with how different the wiggling of different molecules are. So here's something interesting. If I were to pick out only one molecule, I'm going to now isolate my system right here, and I've only drawn a single molecule inside that box. I can't talk about the temperature of that molecule. Temperature as a concept isn't defined on the level of a single molecule. So I can measure its wiggling and everything like that, and that's not enough to give me a temperature. It's not that there's some sort of flaw in my ability to measure it or my ability to understand it. It's that fundamentally, temperature isn't about a single thing. It just doesn't exist. It's like a nonsensical question for me to ask, what's the temperature of that one molecule? Okay, it's not defined. I'm asking a nonsensical question. So temperature, it has to do with wiggling, but big important distinction here. It's the wiggling of all of the particles compared to each other. So let me show you three scenarios, and you'll kind of see what I mean. So in one scenario, this particle wiggles like this, okay? And this particle wiggles like this, and this one next to it wiggles like this. And I hope you can see I've tried to draw kind of the same wiggling pattern. Okay, that's scenario one. In the next scenario, maybe this first particle starts out the same. The second particle does something like this. And the third particle, then again, does something that looks kind of similar to the first particle. All right, and then the last case is when they would all be wiggling in different ways. So I'm trying to make these different. Okay, hopefully that's sufficiently different. So in this scenario, the temperature is lower. In this one, it's a little higher. And in this one, it's the highest. Okay? So as temperature increases, it's telling us something about how the different particles wiggle differently than each other. It's not enough to just be wiggling. There are instances where all the particles are wiggling a lot, but they're wiggling all together, and it's still very low temperature. Okay, like in labs, I have colleagues that work in condensed matter physics and stuff, and they deal with this every day, where the particles, sure, they're wiggling, but that's not enough to give them a temperature, a high temperature. They can be wiggling fast, still not a high temperature. They have to be wiggling fast in opposition to each other, in different directions, all right? So with these two understandings put together, this is what we mean when we say that temperature is about the little motions, the little wiggles of individual particles, all right? This is kind of an overview definition. Now, you might be asking, well, we've got particles wiggling, but I thought that that was energy, kinetic energy, right? So what's the difference between the energy of a particle and its temperature? Well, as we're going to see, and next talk I'm going to talk about pressure, both temperature and pressure are pretty closely tied to the energy. So if you were thinking that, well, aren't we talking about energy here? Yeah, you're pretty much right. We're basically talking about energy. In fact, temperature, more or less, and this is not an equation, this is more giving you like a units type of thing, but temperature is about like the energy, just you divide by the number of particles. Okay, and there's coefficients in there to actually set like what ratios we need and stuff, but this is roughly it. So you'll see that it's not that far from energy. All you do is you have to account for how many particles. You have to divide by the number of particles. So that intuition that energy and temperature kind of line up with each other, they seem like, aren't you talking about the same thing? Yeah, we kind of are, all right? Temperature is very close with energy. And we're gonna get to pressure next time, but it turns out that pressure is something like an energy over a volume. Okay, so here we're dividing by a number and here we're dividing by volume. Again, not exact equations, don't even write these down, but these are just to show you how closely temperature and pressure are related to that intuitive concept of the energy of the particle, all right? And when we talk about the first law of thermodynamics, we're gonna talk more about how do we exactly define the energies and what's the internal energy versus the energy of the center of mass and stuff like that, okay? So, the next point is if more wiggling in different directions equals higher temperature, let's think about reversing that back and going down to lower and lower and lower temperatures. And so there are two ways, and they kind of go together in physics. These two things kind of happen at the same time. Two ways to lower temperature. Number one is obviously wiggle less, and number two, wiggle less in opposite directions. Start to wiggle more in this together, all together in the same direction. And those two things kind of happen together in nature. So as temperature lowers and lowers, things start to move less and less. They start to move slower and slower and have less and less energy, to the point where you've almost got no movement. And that's what's called absolute zero. All right, so I'm gonna erase this. And I'm just gonna draw very little wiggles, okay? These things are barely moving. They're just barely vibrating. So this, and then, okay, let me also add to the scale if they were stopped. All right, my top drawing here is the particles totally frozen. And this is what I want to label absolute zero. All right? Now, here's the important thing that you got to remember about absolute zero. It is impossible to get to it. So, quantum mechanics, where should I write this? And I'm not gonna, this is not a quantum mechanics course, okay? But I'm just gonna give you a result from quantum mechanics. This is the study of the individual atomic structures, and quanta, that's just the word for small things, breaking things into small pieces. So this is the mechanics of very small things. And it's a big field, you guys have all heard of it. And one of the results from it is that absolute zero, absolute zero cannot be achieved. Nowhere, no way, not in the universe, not for all time, will we ever actually have anything at absolute zero, where there's zero motion. And this is a proof. That's proven. Quantum mechanics gives us the ability to prove that. Every atom is wiggling just a little bit. So when we're talking about trying to get things as cold as possible, understand that we can still get really, really, really close to absolute zero. But perfect absolute zero never can be achieved. So how close have we gotten to absolute zero? We've gotten, so that's what this diagram is. This is going to represent a system that's like as close as we can get to absolute zero. We have gotten to within about 1 picokelvin. So this means about a trillionth of a degree. Of degree in the Kelvin scale, okay? And it's actually interesting, this has been done on Earth in a lab by humans, and it's the coldest spot in the universe. So that's a fun fact. It turns out that the hottest and the coldest spots in the universe right now are both on Earth. There's crazy stuff out in space, it gets crazy cold, they're like crazy huge stars and quasars and everything, and yet the hottest temperature here on Earth, it's in the Large Hadron Collider that's in Switzerland, and the coldest place, it's also here on Earth in the whole universe. Okay, so the coldest place is stuff like this, where in labs they really, really, really pump the energy out and get those molecules almost down to where they're barely moving. All right, and so as technology improves, we're going to keep knocking this temperature down and down and down, closer and closer to zero. There's no limit to how close we can get. We can keep getting closer and closer, and as we zoom in, keep narrowing that gap. It's just that we'll never get there. We'll never get an atom to totally stop moving, okay? All right, so now I want to review our discussion about the scales. The temperature scales. Number one, because now that we've had the background, the theory behind what temperature is, maybe it can be appreciated more. And two, I want to have it recorded on a lecture format. So even though we did talk about it in lab on Friday. So I'm going to use up most of the board here and draw a giant scale. So this is just a giant temperature line. And right here, I'm going to put 0 Kelvin. Now Kelvin is our base unit here that we're going to use in temperature. Okay, this is the base SI unit for temperature, that's why I'm starting with. And this 0 Kelvin is absolute zero. So when I say 0 Kelvin, I mean absolute zero. That temperature where motion stops, the one that can't be reached. That's at that end of the scale. And then as we go up the scale, somewhere about here, we're going to hit 273.15 Kelvin, all right? And Kelvin is the only unit that doesn't get a little degree symbol with it. All the rest say degrees. Kelvin is just a K. Okay? 273.15 Kelvin. And then if I keep going further, this is 373.15 Kelvin. And I've labeled these 2 points for obvious reasons that you'll see in a second, but right here is water freezes, and right here is water boils. Now there are a few little asterisks on this relating to, can we measure it precisely, and how does it change for different types of water? The precise measurement might be off by like 1/100 of a degree or something, but this is in the ballpark, and this is what chemists use and stuff like that. So I'm not going down to infinite precision here. So water freezes at this, and water boils at this. And because of these 2 special places, the freezing and boiling point of water, that's what led people to introduce the Celsius scale. So right here, this same mark is also 0 degrees Celsius, and here at the boiling point, it's 100 degrees Celsius. And so all of this is metric. This is the metric system. The way to remember that is because the metric's nice, it does everything in powers of 10, and so going from 0 to 100, we like that, okay? And so you'll see that 0 degrees Celsius is obviously not 0 degrees Kelvin. It's not anywhere near the end of the scale. It's the same scale, but it's way shifted. The 0 point has been brought way up. And that's why in Celsius we can go negative temperatures. But in Kelvin, obviously, everything is coming up positive from 0. All right, and then this is broken into units, and I'm gonna exaggerate them, okay? But there's gonna be 100 of them. Each unit, each division mark is a degree, and there's gonna be 100 degrees in between this and this mark. So now I'm going to do standard or imperial, okay? Imperial units. And I'm going to start at absolute 0 because it's a logical place to start. Okay, any temperature system that we want has to start at absolute 0. And for the standard system, the 0 point's called Rankine, okay? 0 degrees Rankine. And then we come up here, and what do? At the freezing point of water, well, just like Kelvin, we can label where it is. And this is the number I always forget, 491. So water freezes at 491.67 degrees Rankine. And then water boils at 671.67 degrees Rankine, okay? So again, just labeling on that Rankine scale. These are way up in here in the hundreds, boiling point, freezing point of water. Okay. Now, the Fahrenheit, which is what we normally use, is based on the Rankine scale. And when we're used to this by now, this is 32 degrees Fahrenheit, freezing point, and this is 212 degrees Fahrenheit. And these numbers are chosen for historical reasons. But notice, here we started our freezing point with the 0 in the Celsius scale. Fahrenheit, we couldn't even be bothered to do that. Okay, we put 32 degrees at the freezing point. So the true 0 is somewhere down here a little bit. 0 degrees Fahrenheit. And again, when I say true 0, I mean in the Fahrenheit scale. I don't mean absolute, which is obviously way down at that end. Okay? So notice that Fahrenheit it's even more messy because our 0 point is a little further back from the 0 degrees Celsius. All right, and so to convert between these, let me make a box here. This is not part of the diagram. I'm just going to show you the conversion factors. To convert between these, we take Kelvin is equal to degrees Celsius plus 273.15. Rankine is equal to degrees Fahrenheit plus 459.67. Now to convert between Celsius and Fahrenheit, we have degrees Celsius equals degrees Fahrenheit minus 32 times 5/9, multiply it, and then finally degrees Fahrenheit is degrees Celsius times 9/5 plus 32. So, like I mentioned on Friday real quick, this change of 32 degrees, how we're subtracting it here and adding it here in the formula, you can see that on the chart. It makes sense. It's this gap between the 0 here and the 0 here. They're offset by 32 degrees. Okay, I hope you can see that. The 5/9 or 9/5 comes from the fact that the degrees themselves are different sizes. So I drew these exaggerated big ones up here. Well, here, I'm going to exaggerate them as well, but they're smaller. So each degree, this same temperature unit is chopped up into smaller degrees. And that's what makes us have to multiply by this factor of 5/9 or 9/5. All right? The last thing I want to point out about this is that, and our book spends a lot of time on this. I'm not going to spend nearly any time on this, but if you read the book, this is kind of explaining this. Okay, I could write down a third scale, and I could make my own scale. So I hope you're seeing, if you look at these, they're kind of arbitrary. They're kind of just picked. Like somebody just said, oh, that sounds good, that number, we'll go with it. And there are reasons behind it, but all the reasons are kind of arbitrary, all right? So this could be anything. As long as my 0 matches absolute 0,